Hey, welcome back, everybody. All right, I was looking at the calendar. It looks like we are on the halfway mark. So we're going into the fourth week, I believe. Let's double check that. Yeah. Anyway, the point is the finals coming up pretty quick, end of the semester. So hopefully you're on top of things, keeping up with your stuff and so forth. A reminder that homework assignments are available all the way to the end of the semester, but with a penalty with that. Okay, so if you're not done them, you can still do them, but there will be a penalty involved with that particular assignment. Let's see what else. Just also, second reminder is one, I moved the the exams. I looked at the schedule, kind of a little bit set behind, no problem. I just shifted everything over to a Friday, Saturday scenario, meaning that the exams will be due, like the next one will be due next Saturday, but they'll be available and open on Friday. So Friday morning at 7 a.m. If you want to take it, go for it. If not, they'll close that Saturday at 11 p.m. And I did that with all of the other remaining exams to try to spread them out. Make sure you get too much of it, but given 8 weeks to work with, it makes it a little difficult. I try to spread out the homework too. I moved that around as needed. As I stated, the schedule in the beginning is adjustable. It depends on where we're at and how we're proceeding. So I will adjust the homework as necessary. Always remember that I won't make it due until after we're done with that particular chapter. Okay. All right. Any questions, comments, concerns? The plan today is that I'm going to finish 8, and then I'm going to have some additional information about chapter 8, and then we'll jump into chapter 9. Chapter 9 is fairly short too. Okay. All right, well, let us continue with chapter 8, where we were talking about nomenclature, okay, and naming compounds. This one here is we are creating formulas that contain polyatomic ions, okay? To refresh your memory, periodic table, polyatomic ions. We're in the bottom left corner here. There are some common polyatomic ions. That list is by no means, all of them. There's a lot more, but these are the most common ones, at least the ones we're going to work with. Okay. A takeaway from that is that they come as a unit. Okay. And if I need more than one unit, then I need to put a parenthesis around the unit, whichever it may be, and then use as a subscript the number that I need extra, greater than 1. If you only need 1 unit, you don't need a parenthesis. Oh, by the way, I forgot my screensaver here. I did find an image of the D and the F orbitals. I made an announcement for your viewing, so you can see there that there's some crazy looking images with respect to the D and the F orbitals. Remember that the shape is determined by the formula or the mathematical formula that was used to describe these orbits. All right, just FYI. So let's go back. So now we're going to be writing formulas with polyatomic ions. Okay, so here they're giving you one magnesium, which one, if you look at it, it's not telling you what the charge is. We're still dealing with ionic compounds. Okay, so these ionic compounds will have these metals will have a charge. So the first thing we got to do before we even proceed, if the charge isn't given, then we need to determine what the charge is, because we're going to put them together such that we have enough cations to cancel out the number of anions. Okay, and so we got magnesium, is a group 2 metal, okay? And therefore will possess a +2 oxidation state, +2 charge, okay? Because it's a +2 metal, Roman numeral 2A metal. It's again a metal, it will lose electrons, and being in group 2, it will lose 2 electrons, okay? And then we got the hydroxide, polyatomic ion. That's called the hydroxide. Yeah, be familiar with the names given in that table with respect to the polyhydroxide ions, because we don't change the name for the polyhydroxide ions. They are what they are, what they're given. So this one's called hydroxide. And it's a very important polyatomic ion. We're going to learn a lot more about this in the next chapter. Okay. So anyway, we gotta put these together. You can see that I got a negative for the hydroxide and a +2 for the cation. Okay. So that tells me that I need 2 hydroxides to cancel out the +2 of the +2 charge or oxidation number for the magnesium ion. Since we need 2 of these polyhydroxide ions, we're going to need a parentheses. Therefore, to write the formula is Mg parentheses OH subscript 2. Okay. Now I've seen this before, and this is totally incorrect, thinking that we need 2 hydroxides that we end up with a subscript O2 and an H2. That is not correct. Okay, that is something else. I have no idea what that is, but that is not the hydroxide ion. Remember, these polyhydroxide ions are a unit. They're not separated. We don't change the name, so that wouldn't be called like hydrogen oxide, anything like that. It would be the hydroxide. Okay, so we draw that out, and that is our formula. Okay. Okay. Second one, this is called the phosphate, PO4. Okay, let me go here. Magnesium hydroxide. That is the name. Okay. Notice there's no Roman numerals, which brings me to a point. No Roman numerals with respect to the metal. Magnesium is not magnesium Roman numeral 2 hydroxide. It's simply magnesium hydroxide. Why? Because the metal is part of the 16 that have an exact, a constant oxidation number. Remember that list I went through? The metals in group 1, the metals in group 2, okay? Then I added aluminum with a +3, zinc with a +2, silver with a +1, and cadmium, Cd, with a +2. So there are 16 metals, okay? Those group 1, group 2, plus the 4 gives you a total of 16 metals that have a constant oxidation number / charge, okay? Therefore, those 16 right here do not use Roman numerals, no Roman numerals when we name them, okay? And that means all the other metals that we have a slew of, if we need to use them, would require a Roman numeral to describe the oxidation state for that particular metal, okay? So keep that in mind. All right. So we're here, we got K, which is potassium. Potassium is a +2, +1 metal, group 1A metal. Therefore, it has 1 valence electron. Therefore, its oxidation number will be a +1, okay? So now I see here, this is called the phosphate, PO4. Check on your polyatomic ion table. It has a -3 charge. So that tells me that I'm going to need 3 potassium cations to balance the -3 of the PO4 phosphate. And therefore, its formula would be as follows. Okay, K2PO4. Notice we only use one PO4 phosphate ion. Therefore, we don't need a parenthesis. Okay, straightforward, no parentheses. So this would be called potassium phosphate. Okay, potassium phosphate. Okay, let's take a look at the next one. We have Ag, which is silver. Okay, silver is part of the 16 that has a constant oxidation number. Specifically, it has a +1 charge. And then we have the SO4 -2. That is the sulfate. Okay, so we need 2 silvers ions to balance out the -2 of the sulfate. Therefore, its formula would be Ag subscript 2 SO4. Okay, notice here that we are coming up with the formulas. I'm giving you the name, but be prepared to be given the name and work backwards to get the formula. So this one here is silver sulfate. Okay, sulfate. All right, let's take the next one, number 4. We have calcium, okay, which is a group 2A metal, 2 valence electrons, therefore has a +2 oxidation state when it becomes ionic. And then we have the nitrate. This is called the NO3 is the nitrate, and it has a -1 charge. That means that we're going to need 2 of the nitrates, okay, which tells you that I'm going to need parentheses. So here we go. The parentheses around the NO3 nitrate ion, and then the subscript 2. Okay, meaning telling us we need 2 nitrates. So we have a total of 2 nitrogens and 6 oxygens there. We're counting the atoms there. And that name would be calcium. Okay, nitrate. Okay. Right now we're dealing a lot with the 8-ATE, but we also have ITE. We have some other ones that where I'm going to go through a little exercise to kind of help you out with the what these are called polyoxy ions or anions because they have oxygen in them. Okay, I'm running out of space here, but we'll continue. All right, the next one we have copper 2. So that is telling you that the oxidation state for this copper that you're utilizing is a +2, okay? That Roman numeral belongs to the metal, and it tells you what oxidation state it is. So you got a +2, and then the CO3 -2 is called the carbonate, okay? That's a carbonate polyatomic ion. And so we got a +2 and a -2. That's a straightforward 1-to-1. They come together as a 1-to-1, right? And therefore, the formula would be straightforward, where we got CuCO3, okay? And if we were naming that, obviously it'd be copper, Roman numeral 2, carbonate. Okay, notice something. If this was, say, Roman numeral 1, then that tells you that you are using copper +1, okay? And it's still the carbonate. So that tells you also I need to put copper and carbonate together, that I would need 2 copper 1s, right? And so its formula will be Cu2CO3. And what these two share, that is, these 2 compounds we just made, is their base name. They share the base name, and that both of them are called copper. Okay, where they differ is that Roman numeral 1, carbonate. Okay, totally two different types of compounds here. One is a copper 1 ion, one is a copper 2 ion. A copper generally has like a greenish color. The other one has a very beautiful blue-white color, which is kind of ironic in my case because as a child growing up in Superior, Arizona, we used to have a lagoon that the mine utilized for a variety of things. And in that area, there used to be pockets of very blue, beautiful looking water. And as kids, we thought that was cool. To us, that was the ocean. All right. We would play in that stuff. And we thought that was cool. And I didn't realize till later on that those were copper ions in there, which in high concentration are not good for you. All right, so see the difference in how you can distinguish between the two totally different compounds here, because these copper is not part of 16. They have a variable oxidation state, and we have to have a way to distinguish which one we're talking about. And in the old nomenclature, you used to give it the cuprous and the cupric, which was kind of confusing and kind of ambiguous. And so this way, using Roman numerals, there's no ambiguity. It knows exactly what compound you're dealing with, okay? All right, so let me clear up this mess a little bit. All right, the next one. Oh, no, okay. So the point being here is when you're dealing with polyatomic ions and you need more than one, remember to use the parentheses and then the subscript, which designates that subscript and designates how many of those polyatomic ions you need that are 2 or greater, okay? If you only need one, no parentheses is necessary. Now notice here that we did specific formulas, but you can start mixing and matching. For example, I can easily take the magnesium and tie it up with the phosphate or the sulfate or the nitrate and guess what? The carbonate, okay? And so I have magnesium phosphate, magnesium sulfate, magnesium nitrate, magnesium carbonate. I can do the same with any of the metals, potassium with hydroxide, potassium with the sulfate, potassium with the nitrate, potassium with the carbonate, et cetera, et cetera. So now you're building up your database, okay, of the compounds that you're beginning to become familiar with, being able to put together and name. So you're probably in the few hundred list here of all the metals, because this is just a few of the metals. Think of the metals that you have on the periodic table. You have a whole slew of them. Okay, so you can start creating a large database. All right, so let's talk about naming ionic compounds. And the name, again, depends, which is what I've been talking about, is whether that compound has a fixed or a variable charge, okay? Now, if it's a fixed charge, like I stated, then it's simply the name of that metal with no Roman numerals, okay? And there's only 16, that's what I'm trying to help you out here. There's only 16 metals that we have to deal with. And let me refresh your memory who those 16 are, because I got them here in red, in a red box. I got group 1, group 2, respectively a +1 and a +2 charge. And then the one aluminum and zinc, silver, and cadmium. One way to help you remember is kind of using, like you start at aluminum, and if you go at an angle to the left, okay, and then you kind of make like a little wedge, if you will. Start aluminum, go diagonal to zinc and silver, and then cut back to the right with cadmium. Okay, those are the 4 there, okay? And plus the other 12 gives you 16, and in blue I've circled their respective charge. +1, +3 for aluminum, +2 for zinc, +1 for silver, +2 for cadmium. Okay, so those 16 do not require Roman numerals. Okay. I repeat, those 16 do not require Roman numerals. All the others do. Okay. All right. Naming, I've introduced the name part. As far as the metal itself, the metal name remains whatever it is. Sodium, when it becomes sodium atom and becomes loses its electrons, they become an ion, it still remains the name sodium. It is the anion that changes its name. Okay, so chlorine, which is the element, when it becomes the ion, we change the name to chloride. Okay, so that one, the name here is sodium chloride. Now you got potassium chloride. Now being chlorine, guess what? Go through all the other halogens, the fluorine, the bromine, the iodine, same thing. Their name becomes fluoride, so you can get sodium fluoride, sodium bromide, sodium iodide. Okay, we can take any of the metals and combine them. We got the lithium, sodium, potassiums, rubidiums, and so on and so forth. Beryllium, magnesium, calcium, and combine them with any of the halides that we got here. Okay, so we're starting to build up our database. So that's sodium chloride. All right, let's take a look at this one. First of all, we got potassium. Okay, K is potassium. And then we got Br, and we'd be tempted to call it bromine, but keep in mind, it's not Br subscript 2, which would be bromine. That's elemental bromine. The fact that you got potassium first, followed by the nonmetal, tells you have an ionic compound. Therefore, this becomes bromine, becomes bromide. So we have potassium bromide. Okay. Next one, we have Mg, which is magnesium. And then you have O, which is oxygen, but it's not, again, it's ionic oxygen. It is a group 6 nonmetal. It gains electrons and becomes and has a -2 charge. Okay. And so then we change the name from oxygen to oxide. So this becomes magnesium oxide. Calcium is the metal. The nonmetal is fluorine. We may be tempted because we think of fluorine, oh, it's diatomic, okay? And you see a subscript 2, you might be tempted to think fluorine is diatomic. It's not. The fact that you got calcium first, any metal first, and then followed by any nonmetal tells you you have an ionic compound. So we have to change the name of whatever the nonmetal is to the "ide" ending. So this becomes calcium fluoride. Notice something, no Roman numerals here. Potassium, magnesium, calcium, all part of the 16. No Roman numerals with respect to the name. Okay. Lithium as a group is the +1 metal, group 1A metal. And then we got sulfur, which is the nonmetal. Okay. As in the case with oxygen, they belong in the same group. As in the case of oxygen, it will also gain 2 electrons, okay, to become the anion, having a -2 charge. And also, as in the case of oxygen, the name changes to sulfide. Okay, so this is simply lithium sulfide. Okay, not to be confused. Let's just talk about sulfide here, because we got S, which is sulfur, the element, right? And then we got -2 when the sulfur by itself, okay, its name changes to sulfide. Okay, so the ide tells you that is just the element by itself, whatever it may be. In this case is S, just like oxygen. Oxide means it's just oxygen by itself, being O -2 for the ion. Now the other, if you look at the polyatomic ions, if we take that sulfur and we attach to it oxygens, it still has a -2 charge, okay? But we also change its name and call that sulfate. Look at the polyatomic ion table, very common polyatomic ion. The prefix SUL remains. What changes is the suffix. We go from UR to IDE to ATE. okay? So if you see the name ATE, look at what the first prefix is. That tells you what element, plus the ATE tells you, oh, I got oxygen bonded to that element. In this case, I'm looking to sulf, the prefix for sulfur, and the 8 tells me, oh, I got oxygens bonded. How many? Well, the base name here, and we're going to talk all about this, has 4 oxygens, okay? Now we can remove an oxygen and still maintain a -2 charge, but we have to change the name, and that becomes sulfite. And so when you see the 8 and the ite, the only difference between the 8 and the ite is -1 oxygen. And if it loses more oxygens, then we give it another name, okay? And we'll have a whole little talk about that. Okay. The same is true. We can do the same exercise with nitrogen, okay? Nitrogen, we got nitrogen here as the element, okay? And then when it becomes the anion, it becomes nitride, okay? And then we have nitrate. And then we can remove an oxygen, and that becomes nitrite. It still has a full -1 charge, okay? All right. Now, those here I just talked about, the 8 and the ite, those are polyoxy anions. Let me clear this up here. Okay, here's the next one. Silver, again, is one of the constant oxidation numbers. Silver is +1. Chloride is a -1. Okay, so its name simply is silver chloride. Okay. Okay. Remember, these also 2 things to take away. For the polyatomic, for the 16 metals, no Roman numerals. Second of all, and when it comes to name, second of all, no prefixes at all with respect to all ionic compounds, okay? No prefixes now for ionic compounds. We're talking about di, tri, etc. And so here we would have called number 4, we would have called that dilithium sulfide. Okay, it's simply lithium sulfide. Number 3, it would not be called calcium difluoride. It's simply calcium fluoride. Okay, so no prefixes. It is only the covalent compounds that utilizes prefixes in naming them. You will find sometimes if you read the labels, I don't know why they do this. I think a lot of it is marketing and stuff. They would add prefixes for ionic compounds. And generally, I think that's just marketing, putting names in there for whatever reason. But the only prefix I know is dilithium crystals in Star Trek. Just kidding. Anyway, let's go to the next set. Okay, in naming polyatomic ions, as I stated, polyatomic ions have their own name. We don't need to change them. It's in the table. That's it. We just use the name, whatever it is. Again, we don't use prefixes if we need to use more than one polyatomic ion. Okay. All right. Well, first of all, we have to identify. How can I identify that I'm dealing with a polyatomic ion? Because after all, it's the first time I've seen these things, right? All right. Well, here's a little kind of a tip that may help. All right. Well, we see potassium here. All right. And we got 3 of them. All right. The fact that we get a subscript with the metal tells me, well, the fact that we got a, let me restate that. The fact that we got a metal written first should tell us, oh, we're dealing with ionic compounds, right? Okay, we got a metal first. If it was a non-metal, more likely covalent compounds. Okay, but for 130, we're going to see metal written first. We have a ionic compound. So we look at the next element and we see phosphorus. Well, we need to go a step further and we need to check what's, okay, we might think phosphide, but the fact is the next elements after phosphorus is oxygen, okay? So automatically, if you see oxygen right after that first nonmetal, think polyatomic ions. And so now you're dealing with PO4, okay? Now you know that each potassium is a +1. Why? Because it's a group 1 metal, right? And there's 3 of them. So there's a total of a +3 charge for all the potassiums. What it tells you that this thing over here has to have a -3 charge, all right? And so you see PO4, that should send you to the polyatomic ion table and look for PO4 with a -3. And sure enough, when you do that, you'll find it to be phosphate. Okay? And so its name will be potassium phosphate. Okay? If it was phosphide, okay, if it was phosphide, and if you wrote phosphide, remember, the IDE ending tells you it's simply that element, whatever nonmetal it is, by itself. This phosphide would mean that would be just the phosphorus, or in this case, the phosphide by itself with a charge. And that's not the case here. All right, notice no parentheses around it because you only need one. When you see a parentheses, that right there is a flag to tell you, okay, I'm dealing with polyatomic ions. So that should send you all the way, send you to the polyatomic ion table to determine which one that is. And that is a hydroxide, the OH, if you look at your table. And there's 2 of them, okay? Because the table tells you that each OH has a -1. And if I have 2 of them, I get a total of a -2 charge. What does that infer? That infers that the metal, potassium 2, must be a +2. And then is it normal? Yes. But the calcium, is a +2 because calcium is a group 2 metal. Okay. Let me expand on this, because if you were to look at a formula that was something like this, okay, and you're going to name it, you say, oh, that's potassium hydroxide. That'll be your first indication, right? But check that formula. Does that formula make sense? Okay, because like I explained, you see a parentheses, polyatomic ion. We go to the table, each one has a -1 charge. That means they got a total of -2 charge. That infers, again, that potassium must be a +2, because when I combine the cation and the anion to write the formula, they must cancel each other out. But does that make sense? No, because potassium is a group 1A metal, okay? Which means that it can only have a +1 charge. So this formula will be totally incorrect, okay? All right. So what we have here is calcium hydroxide. Note again, no Roman numerals, no prefixes. We're dealing with ionic compounds. No prefixes for all ionic compounds, and no Roman numerals for the 16 metals. Okay, we got zinc, and then we have sulfur, but immediately, like we did the first one, immediately following sulfur, we have oxygen. That's an indication of polyatomic ion, specifically the sulfate in this case here, because there's 4 oxygens. So we have zinc sulfate, okay? Zinc sulfate. Now, mix and match. We did potassium, but you can hook it up with the hydroxide or the sulfate, and the same with calcium. Calcium phosphate, calcium sulfate. Same with zinc hydroxide or zinc phosphate, okay? Mix and match here. Okay, so when we're dealing with the variable charge metals, this is where the Roman numeral comes in, okay? Now you might ask, well, wait a minute, how do I know what the Roman numeral should be? And my answer is this: you're always going to know what the anion charge is. And also, like I stated, remembering that the total number of cations plus the total number of anions must equal the charge of the whole molecule. Majority of molecules that we present here have a net charge of 0. Okay, I have enough of each to cancel everybody out. So if you know the charge of the anion, okay, and you know the charge of the molecule or the compound would be 0, you can calculate what the metal would be, which metal you're working with. We'll do some examples here. For example, let's take a look at this one. You see Cu, and that's copper. Well, copper is not part of the 16, right? So it does not have a exact oxidation number. It's a variable. But the question is which one, okay? Because remember I spoke earlier, it's either copper +1 or copper +2, okay? All right, so which one? So we need to calculate it. All right, so remember I said the number of cations plus the number of anions equals the charge of the compound, CPD, okay? So in this case here, the charge of the compound is 0, all right? So we can set up a little algebraic equation, that's 0, all right? Copper, we don't know what the charge is, so I can write that down, okay? So that's the cation, that's the unknown, okay? But what do we know? Well, the chloride, we know 2 things here, name-wise. We know we're going to use copper, and we're going to use chloride in the name. Question is, what is the Roman numeral? Which oxidation state is copper? And that's what we're going to do here. The chlorides are group 1, okay? Excuse me, group 7. I was thinking of some now. So they're nonmetals. They end up with a -1 charge. There's a total of 2 chlorides, right? And so being a total of 2, each one has a -1. So it's 2 times -1. I end up with a little general algebraic equation of Cu minus 2 equals 0. Okay. And so we got to solve for Cu. Guess what? Cu, which is copper, is equal to +2. So the oxidation state of copper here is a +2, which tells you that we're using Roman numeral 2, okay? And that's what I mean. You're always going to know, if you don't know the charge of the cation, you know the charge of the anion. And guess what? Vice versa. If you don't know the charge of the anion, you will know the charge of the cation to figure it out, okay? Okay, so we're dealing with a +2 metal here, so its name would be copper, Roman numeral 2, okay, chloride, okay? Again, no prefixes for the chloride, so it wouldn't be dichloride, it's simply chloride. Okay, let's take a look at this one. Well, we don't know which lead we're talking about here, but what do we know? We know that each oxide is a -2, okay, each one. And there's 2 of them. So I set up my little algebraic equation. There's 2 -2s, so it's a -4 is equal 0. The charge of the overall charge is a 0, okay? And so I got P, which is, PB, which is lead, -4. Solve for PB, and that is a +4. So the oxidation state in this example will be a Roman numeral 4 because it's a +4 state. So its name would be lead, parentheses, uppercase Roman numerals, IV, oxide. Okay. All right. Here we have nickel and the Br, which is the bromide. And so we have nickel, okay? We know that the bromides, like we did the chlorides, each have a -1 charge. There's 3 of them. Therefore, we have a -3 is equal to 0 overall charge. So we solve for nickel, which is a +3. So the oxidation state for nickel here would be a +3 state. And so its name would be nickel, Roman numeral 3, bromide. Manganese, okay, then we have S, which we're thinking may be sulfide, but then immediately following the sulfur, we have oxygen, should send you to the polyatomic ions, because there is one there called sulfate, SO4 -2, right? And so I set up my little equation here, and I do this systematically so I can, once I get comfortable, I don't have to set up this equation, but once you can get to the point where you look at the molecule, at the compound, and you actually can figure out mentally what its charge is. So we got a -2 for the sulfate, it's overall 0. That means that Mn is equal to a +2. So we're using Roman numeral 2 to name this guy. And manganese, Roman numeral 2, sulfate. And then again, here we got copper, okay? And then we got copper followed by nitrogen, which you might think nitride, but then we got oxygen following right after nitrogen to send you to the polyatomic ion. I know I sound redundant and I'm repeating myself, but that's okay because I'm trying to get you to look at things systematically to solve the problems, okay? Once you have your own little way here, you can bypass whatever steps and go directly to it. So I got nitrogen, thinking nitrite, I got oxygen immediately following. It's a nitrate or a nitrite of some sort. So I go to polyatomic ion, I find out it is called nitrate. It has a -1 charge, which implies that the copper has to be a +1, because it's a +1 charge, which we use copper, Roman numeral 1, nitrate, okay? And as the case as the others, you can mix and match. You can mix with the lead with the bromide, lead with the sulfate, lead with the nitrate, and vice versa. Nickel with the oxide, nickel with the sulfate, nickel with the nitrate, etc. So you see how we're building up your database with all the different compounds. Now, notice here, everything here with respect to the overall charge of the molecule is 0. And I gave you the general equation, number of cations plus the number of anions equal the charge of the compound, because you can have an example where you have a charged molecule. For example, let's take the sulfate, okay? The sulfate polyatomic ion is SO4 -2. Question is, what is the oxidation state of that sulfur? Okay, well, we do what we just did, except the difference is the charge of the molecule has a -2. And so we got sulfur plus, we have 4 oxygens, and each one has a -2, right? And that is equal to a -2 overall charge. So what do we got? We got S minus 8 is equal to a -2, right? And then we've got S is equal to 8 minus 2, and that is S is equal to 6 plus 6. So in this state, SO4, the sulfur has a +6 oxidation state when it's bounded to 4 oxygens, okay, to create the sulfate polyatomic ion, which has an overall -2 charge. Okay, so that general equation I gave you can fit for all kinds of scenarios. In general, we end up with a single integer whole number, but it's feasible, depending on the molecule, to get like a quarter charge. It's basically an oxidation state that you may have 2 atoms in there, and they split that charge. So maybe it could be half of the total number. So it's a possibility to have a quarter oxidation number, like 1/4 or 1/3. And there's some in the homework problems, there are some examples like that. Okay. So you don't always get a nice whole number. It depends on the molecule. Okay. If it's a single element and you're looking for its charge number, most of the time it's a nice whole number. But if there's two of them, you may not get a whole number. Okay. All right. Oh, well, one more. Sorry. Last one. We got, notice here, we got nitrogen. Okay. So we got CO, which is cobalt, and then we see nitrogen. And we're thinking nitrate or nitrite, right? No. Why? Because immediately following the nitrogen, guess what? No oxygens. So it is just nitrogen by itself. Therefore, it is simply nitride. It is the nitride, which has a -3. And that implies that cobalt has to have a +3 charge here. Okay, because the nitride, nitrogen is -3, and the cobalt must be a +3. So the name is cobalt, Roman numeral 3, nitride. Okay. Oh, okay. I thought I was the last one. All right, a little more complicated, but we can still break it down. Okay. All right. Well, first things first. You see, you have a parenthesis, right? Indicates polyatomic ion. Go to the table and look for that CO3 on the polyatomic ion, and that turns out to be the cobalt, CO3, which is called the not cobalt carbonate, which is that. Okay. All right. Now notice you have 3 of those carbonate ions, and you got 2 irons. So we need to set up our algebraic equation. And so we got 2 irons, okay? And we have each carbonate has a -2, and there's 3 of them. So guess what? We have a -6 charge, do we not? And that is equal to 0. The overall charge here is equal to 0. So that's our algebraic equation. Now we've got to solve for iron like you would do a very simple algebraic equation. Move the 6 to the right by adding +6 to both sides. So we end up with 2Fe is equal to +6. Okay. Now we divide through by 2 to isolate iron. That means that iron in this state must be a +3 charge, oxidation number. Okay. And so therefore, erase something here. Therefore, the name is iron, Roman number 3, carbonate. Okay. Now you can at a glance, look at that formula and determine almost immediately what oxidation state it is by looking at its partner anion and how many anions it has. Okay, because to help you out, that normally when you write the formula, the subscript of the anion, guess what, is the charge of the cation, and the subscript of the cation is the charge of the anion, right? Isn't the anion a +2? Okay. So I could very quickly, once I'm familiar with that and understand that, go directly and say, oh, that's iron 3. Okay. If I'm not sure, then we go through this process we just did to figure out which one it is. Okay. Here, he's either going to give you the name and the formula. Let me back up for a second. Notice here, every example we did here, okay, this is the examples of variable charge metals. They have an oxidation state that we didn't know what it is, and we had to calculate what it was, okay? And then we had to use the Roman numerals. Any of those metals were part of the 16, no Roman numerals. I can't overemphasize that. Okay. All right, here we have strontium and hydroxide. Strontium, SR, is a group 1, group 2 metal, okay? It's right underneath calcium, and therefore it has a +2 charge, okay? The hydroxide has a -1 charge, and guess what? We're going to need 2 of them, which means we're going to use the parentheses. And so I'm going to write them out first, and then we'll clear out my mess and show the typed out information. So that's the formula there. Okay, strontium hydroxide will be the name. All right, here, Au, which is gold. Okay, gold is not part of the 16, therefore we're going to use a variable, a Roman numeral. Question is which one? Well, what do we know? Each chloride has a -1. That means we got a total of -3 for each chloride, which infers that the metal must be in a +3 state. And so therefore we have gold, Roman numeral 3, chloride. Okay. Zinc is one of the 16, it has a +2 charge, and oxygen is always a -2 charge. It's the oxide. So putting these together, we will be simply named, formula-wise, would be a ZNO. That's it. Named zinc oxide. Okay. All right. Here we have the PO4, which is a polyatomic ion, which is the phosphate, and it has a -3 charge. Barium is a group 2 metal, so it would have a +2 charge. Okay. Now we're going to put together a -1, -3, and a +2. What do? We find a common number, which in this case is 6. Okay. So we need a common number, which therefore we need 3 barium ions. It gives me a total +6. And we need 2 phosphate ions, which gives me a total of -6. So those numbers I wrote here become the subscript. Ba3, since I need more than 1 phosphate, parentheses, PO4, subscript 2. Okay. Barium phosphate. Okay, this is SO3. You might be tempted to call it sulfate, but you know, we got a polyatomic ion. Make sure you select the correct name. You'll see in the polyatomic ion table that the SO3 is the sulfite, name-wise. Lithium is a group 1. It has a +1 charge. Okay, that means we need 2 lithiums. So its formula would be Li2SO3, aka lithium sulfite. All right, here we're just given the elements, so we're going to convert them to ionic compounds. The aluminum has a +3, and the sulfur becomes a -2. Okay. As the case with the number 4 here, where we look for a common number, the same is true here. I need a common number. In this case, also it happens to be 6. So I need 2 aluminum ions and 3 sulfite ions. Okay, so that gives me a total of +6 for the aluminum and -6 for the sulfite. And so the formula becomes Al2 sulfur or sulfide 3. That's its formula. Okay, then the last one asks you, just name it. Well, we're given the formula. We don't know what this oxidation state is, but we back calculate because we got a parenthesis here. Sends you to the polyatomic ion table, and you'll find the NO3, which is the nitrate. Each one has a -1, okay? And you have 2 of them. That means you got a total of -2. That infers that this copper has to be a +2, okay? Therefore, we end up with copper, Roman numeral 2, nitrate. Okay. All right, let me clear up my mess. And we get that. And included the names there for your reading pleasure. Okay, so be able to work, both directions, name to formula, formula to name. Remember when to use and when not to use Roman numerals. Okay, when you use any of the 16, no Roman numerals. And remember, for all ionic compounds, no prefixes. Okay, no prefixes. Okay. Here we're asked to give the formula. So we got sodium nitrite. Nitrite. Notice it's not nitride, I-D-E, is I-T-E. The I-T-E, the I and the 8 signal you or should send you to a polyatomic ion compounds. Okay. And we know in order to write the formula, the first thing you got to do is write the ion. We got sodium, which is a +1, and the nitrite, which is a -1. Okay. And so now put them into ionic form. Now you can put them together because that tells you how many of each I need. In this case, it's a simple 1-to-1 because the nitrite is a -1. The sodium ion is a +1. So its formula is simply NaNO2, sodium nitrite. Okay. Nickel 3, this tells that Roman numeral tells you what nickel to use. So it's Ni+3, and the oxide is always a -2. Okay. And so we have two dissimilar charges here. We're going to find a common number. Again, in this case, it is a common number 6. So I need 2 nickels and 3 oxides. So its formula becomes Ni2O3. Okay. For nickel Roman numeral 3 oxide. All right. Magnesium, it's a group 2 metal, so that will have a +2 charge. And then iodide is a halogen, group 7. It would have a -1 charge. Okay. I'm going to need 2 iodides for every magnesium ion. So therefore, our formula becomes Mgi subscript 2. Okay. Magnesium iodide. Cyanide. We did the Lewis dot structure for this, but again, cyanide sends you to the polyatomic ion table, and aluminum has a +3. It's one of the group, the 16 that has a constant oxidation number, and the cyanide is a polyatomic ion with a -1 charge. I need 3 of them, therefore the formula would be aluminum (Cn) and parentheses subscript 3. Aluminum cyanide. Okay. All right, so again, this is like a double arrow. Be able to go in both directions, given the name, go to the formula, given the formula, yeah, go to the name. Okay. Now, when it comes, those are ionic compounds. To take away from that, remember the 16 that have a constant oxidation state. Okay, no Roman numerals there. All the ionic compounds do not use prefixes. Okay, if you're given the name and they want you to write the formula, from the name determine what the ion is, and then put them together with the correct number of cations and anions. Okay, if the charges are dissimilar, find a common number. Most of the time it's 6, but it doesn't have to be 6. Okay, find a common number and then add enough of each ion to get to that common number, just like you're trying to add up dissimilar fractions. You find a common number, convert everybody to that common denominator, and then write the formula. Okay? Now, with respect to covalent molecular compounds, you will have a central atom, okay, which is a nonmetal, and its name is whatever it happens to be. And then after that, you have whatever follows would be what's attached to the central atom, and those elements we change the name. But surprisingly, the name remains the same as with ionic compounds. So oxygen still becomes oxide, be it for example, sodium oxide versus carbon dioxide. This is called sodium oxide, okay, versus carbon dioxide. Okay. Now the corresponding whatever is attached to the central atom with covalent compounds, the name remains the same. Okay, if that was sulfur, that would be carbon disulfide. Okay, carbon disulfide. Very nasty smelling chemical. All right. With respect to prefixes, here, yes, we do use prefixes, okay? Now, these are not ions, and so we start talking about oxidation number because they don't have a full-fledged charge, as in the case with ionic compounds. The other aspect is this: all these ionic compounds that we've been working with, okay? For example, we're going to learn about this. If I were to take sodium chloride in the solid form and I dissolve it in water, what water does is breaks it up into the ions, okay? And that's one character of ionic compounds, is that when we dissolve them in water, they will break up. Now, some ionic compounds break up 100%, just total breakup, some much, much, much less. Regardless if it's 100% or much, much less, all ionic compounds will break some material will break up and dissociate in solution, okay? If we take something like carbon dioxide and we pour that in water, guess what? The formula is still carbon dioxide. It does not dissociate. So covalent compounds, molecular compounds placed in water do not dissociate. Okay, ionic compounds have a full-fledged positive, full-fledged negative charge. Water goes in there and breaks them apart. In covalent compounds, we don't have a full-fledged charge. We have a partial. Remember, partial positive, partial negative? We have a dipole bond. We didn't break that bond apart. They're still intact. Okay, and that's one of the main differences between the two. The only exception to covalent compounds that dissociate completely is what we're going to talk about next chapter. Those are acids like hydrochloric acid. Hydrochloric acid, the same acid that's running around in your stomach, is a covalent compound. We denote these acids because normally we've got an H in front of it, okay? And when they break up, they actually break up into the ions, okay? Some of them break up 100%, become very strong. Some of them, like vinegar, which is an acid, are not 100%, much, much less, but nevertheless do break up. All right, but more on that later on. All right, so the prefixes that we utilize are given here: mono, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nano, N-O-N-A was 9, and deca for 10. Okay, but All right. And those are the prefixes that we utilize. Now, we we have a nonmetal, the first one, the central atom. Okay, we have its nonmetal name, and it may have a prefix or not. Okay, depends how many you have. And so you have the prefix plus the nonmetal name, and then we add to it the second nonmetal name. We may have a prefix, okay, and then we use the ending "ide," okay, at the end of it. For example, if the first nonmetal is by itself, we don't use the mono, okay? But if the second nonmetal is by itself, we use the prefix mono. That's why that means for one. That's where you might think, well, wait a minute. All right, let me refresh your memory. Okay. Carbon dioxide. Okay. CO, carbon monoxide. Okay. So that's what we meant here. So don't use mono, so it wouldn't be monocarbon, it'd just simply be carbon. But the second nonmetal, if it's one by itself, we use the prefix mono. Okay, so technically, water, because by convention people write it as H2O, it should be really written O and then H2, but that's okay. Technically, this is called dihydrogen monoxide. And that's what I mean. If you look up that word on the internet, dihydrogen monoxide, you'll find the hazards of this chemical and how bad it can be, which, could be, if you got a lot of it and you can't swim, that could be a problem. Anyway, it's really surprising what you find out there. All right, so let's proceed with some examples, okay? This one I've done at length. This is carbon, okay? First nonmetal, carbon, right? We don't add mono. Then we look to the next atom, so that would be oxygen, which becomes oxide. Then we look at the prefix, if there is one, and there's two of them, so it becomes carbon dioxide, okay? As in the case of the ionic compounds, be able to go from the name back to the formula and vice versa. All right. Here we have carbon and a single oxide, so carbon monoxide. Okay. All right. Well, here we have my suggestion is systematic approach. Okay. We got phosphorus. Phosphorus is the central atom. It's the first one. So, and there's two of them. But the base name is phosphorus, which I would write. And then we got oxide. Okay, so that's the base name, the parent name, if you will. Now I go back and check. You see there's, prefixes. Well, we have two phosphorus, obviously that becomes di. And then we have 5 oxygens, and then we have pent. Now, here's the deal. I'm not an English teacher, but technically, when we combine penta and oxide, we got 2 vowels coming together. The egg is supposed to get dropped, and then you just combine them to pentoxide, okay? If you inadvertently forgot that and you just left the A, I'm not going to count you off for it, no big deal. But correctly, if 2 vowels come together to form a word, like the penta and oxide, one of the vowels gets dropped. Normally it's the A gets dropped with the prefix. So it would be, this name would be diphosphorus pentoxide. And unfortunately here it did not get dropped, all right? All right, here we have phosphorus and we have 3 fluorides. So we have phosphorus fluoride is the parent name. And now we add the prefixes. So it's 1 phosphorus and there's no mono, we just leave it alone. And then 3 fluorides, which makes it trifluoride. Oh, come on. So phosphorus, trifluoride. Okay. Iodine is the central atom. Okay. And the fluorides are yours. So the parent name is iodine fluoride. And then we give it the prefixes. There's only 1 iodine, but there are 7 fluorides. So we got heptafluoride. So it's iodine heptafluoride. Can anybody do a quick calculation and tell me the oxidation number of iodine in this state? I want you to guess it. Actually, don't have to guess. You can calculate. What do you think the oxidation number is for the iodine in this state when it is iodine heptafluoride? Anybody want to get us? Well, fluorides each are negative 1, right? So there's a -7 total. So what does that mean that the iodine must be? In what state? What oxidation state? If there's 7 negative ones around the iodine, what must the iodine oxidation number must be? +7. Yeah. +7, exactly, Amy. Okay. What about, take it one second, what about the phosphorus here? What would be its oxidation state? What we got? Exactly, +3. Don't forget the +3, because when we talk about oxidation state, we got to be specific. It's a +3 or a -3. Obviously, totally different numbers, but that's correct. Amy and Eduardo. Now I'll let you work on the oxidation state for phosphorus in this state. Okay, the oxide is still a -2, and there's 5 of them, so that gives you a total of -10, and there's 2 phosphorus. What must be the oxidation state for each phosphorus? That's correct, +5. Each one, so there's 2 phosphorus, there must be a +5. And here's something interesting, you even go back calculate for carbon. Remember, carbon is in group 4, and depending on how it's bonded, it can lose 4 or gain 4. What would you say its oxidation state is here when it's combined with 1 oxygen? Okay, the oxides are still -2. So what does that imply that carbon must be in what state, oxidation state? It must be a +2. That is correct. It's a +2 in this state, its oxidation number. And then over here with carbon dioxide, there's got to be a +4. Okay, because each oxygen is a -2. We're getting -4 up there. Okay, that's good. All right. And so, given the formula, write the name and vice versa, like I said before. So, for example, who wants to take a shot at this? Okay. My suggestion is to first write the base name. Now, bromine, Br is written first, so that's a central atom. Okay. And so, being a central atom, it does not change its name. It remains bromine. Okay. If it followed whatever the central atom, then it would be bromide. But right here, it's bromine. So there's 3 of them. They're treated as a central atom. okay? And so the base name will be bromine and then followed by oxygen, which becomes oxide. So the base name would be bromine oxide. That's the parent name. Now go back and add the prefixes, and you got the name for the molecule. You got 3 bromines, so it's tribromine, and then you got 8 oxides, so its name would be octoxide. Tongue twister, because they're related. Okay. Now here, if you did the oxidation number, it's an example where you don't end up with a nice whole number for oxidation state. You end up with a fractional number for the bromine. There's 3 of them. There's a total of -16 for the oxides, and -16 divided by 3 gives you a fraction of what is the oxidation state of each bromine, and it's distributed amongst each one. That number is distributed amongst the 3 bromines, I should say. All right, similar scenario. Who wants to take a shot at that one? Break it down to its parent name, and then add the prefixes. You want to give it a shot? What would be the parent name? Well, you got phosphorus up front, followed by sulfur, which becomes sulfide. So the parent name, the base name will be phosphorus sulfide. Sulfurs are all by themselves, so they become sulfide, just like the oxygens were by themselves, they're oxide. So the parent name is phosphorus sulfide. Then go back and add the prefixes, and you should end up with tetraphosphorus heptasulfide. Okay. Oh, here's a nasty smelling gas. If you ever driving behind a car and the exhaust comes out and you smell something like kind of rotten egg, that's what you're sniffing. Then this guy goes up into the atmosphere, reacts with the moisture and oxygen and so forth. We end up with sulfuric acid up in there in the rain, and then that comes in next time it rains, it drops down. You have acid, you have what's called acid rain, and it dissolves a lot of stuff over time. Plus, it causes metals that are locked in the soil to dissolve, which get into the water system, and then we got all kinds of contaminants. Okay, parent name, sulfur oxygen, sulfur oxide. Okay, prefixes, we got 3 oxygens, so sulfur trioxide. Okay, sulfur trioxide. Okay, how about this one? We're given the name, we want the formula. So we work it backwards. Before we're given the formula, we get the parent name, then the prefixes. Here, we write the parent formula, then we add the prefixes. Okay, work it backwards. So we have iodine, okay, which is I, obviously, and then we have fluoride, which is F. And we come back, we only got 1 iodine, but then we got the hexa, which means we got 6 fluorides. So that would be the formula for iodine hexafluoride. Okay, same scenario. First, write the parent formula. We got chlorine, which is Cl, and then oxide, which is O. Okay, now come back and write the prefixes. We got penta, which is 5, and then di, which is 2. Okay, So that is our formula, Cl2O5. Okay, now here we're writing, getting the name. So we first write the parent formula, name that is. We see we got phosphorus and we have iodide. Okay, so it's phosphorus, iodide. Then we go back and write the prefixes. There's 2 phosphorus, so that becomes diphosphorus. And then there are 4 iodides, so it becomes tetra, prefix is tetra. So we got tetraiodide, tetraiodide, diphosphorus, tetraiodide. Yeah, some of these can be tongue twisters. All right, reminders. Prefixes are only for the covalent compounds, okay? Roman numerals are only for the variable charge metals. Okay, the 16, group 1, group 2, and then include aluminum, zinc, silver, and cadmium, all have fixed oxidation numbers, charges, no Roman numerals for them, okay? And then polyatomic ions, which are found in your table, we don't change the name. So NO3 negative is nitrate. I know sometimes it gets, people want to take the NO3 and call it nitrogen trioxide ion, and that's not correct. It has its own name called nitrate. Okay. So knock these out here, try them. We got, try these at home. Okay. BaCl2, anybody want to do a shot at that one? Or you can do it now. We're knocking them out now. BaCl2, what do we got? Anybody want to take a shot at the first one? Okay. What do we got here? All right, barium chloride, that is correct, Amy. All right. So I don't think I have them separate. How about NO2, number 2? Okay, the parent name would be nitrogen, and then we got oxide. So half of the answer will be nitrogen oxide. What will be the other half to make it correct? Nitrogen dioxide. That is correct. And then Fe3, and in parentheses PO4 and parentheses 2. Okay. We know it's iron. We see PO4, we see parentheses. So you see parentheses, sends you to the polyatomic ion table. And look for the PO4, which becomes phosphate. Okay. So that name is set, phosphate. Okay. We don't know prefixes because we have ionic compounds here. So then we go back to iron, and the question is iron part of 16? No, it's not. So therefore we have a variable oxidation state. And which one would it be? What is the oxidation state of iron in number 3? It's a +2. That's correct. So being a +2, now we can name it. That would be iron, Roman numeral 2, phosphate. Okay. Number 4, you have iodine and oxide. That is the parent formula. They're asking you to give you the name. They want you to write the formula. So we have diiodine tetroxide. Okay. So I and O are the parent formula. Now go back and give it the prefixes. So you got 2 iodines and 4 oxides. So the formula will be as follows. I2O4. Then silver sulfate, polyatomic ion, has the SO4, has a -2 charge. Silver has a +1 charge. We need to have 2 silvers to give it Ag2SO4. And then nickel 3 sulfide. Here we have 2 dissimilar charges. So we've got to find a common number. Again, in this case, it's 6. So we need 2 nickels and 3 sulfides. So the formula becomes Ni2S subscript 3. Okay. All right, well, we got a worksheet there. Okay, don't forget to do that. Let's take perfect timing. Let's take a quick break. All right. And let's come back at 15 minutes or so. And I'll stop things here. We'll continue with chapter 9. Okay. All right. I'll see you in a bit, 15 minutes. I got my computer says 2:28. I don't know, call it 2:45. 15 minutes. All right. Be right back. Okay, I'm back. I'm just reading the question. No, that worksheet is the one from chapter 8. There isn't, no, it's, if you go into the module from chapter 8, there is a worksheet. In fact, all the chapters have their own individual worksheet. It was just a reminder to work through that and help you through the nomenclature. Okay. All right. You're welcome. No problem. All right. Now, what I want to do is instead of jumping into the next chapter, there is in the module for nomenclature some other files that I put in there to help you out with additional resources when it comes to naming. Now, we did talk about shortly about these polyatomic ions, specifically the sulfate, the nitrate, and sulfite, and so forth. So I want to go briefly and talk about these, what we call polyoxy anions. Where you probably see them come into play is in the nomenclature exam, and that will help you with respect to naming them. So what I'm going to do is share with you one of the files. Specifically, it's a Word document file found in the nomenclature module. Okay. Now there are, I gave you some links for some YouTube videos concerning this topic. Okay, and the turn to the way presented. I will do a PowerPoint slide here to kind of show you how we can go through and determine these sulfates and sulfites and hyposulfites and so forth. It can be a little bit confusing, but what I'm going to attempt to do is try to make it less confusing. Now, we use only a certain part of the periodic table, okay? And we use boron. If you look here, we've got boron, carbon, nitrogen. And then we use underneath the group 4 elements from carbon down to 10, okay? And then nitrogen down to antimony. And then we don't use oxygen, obviously, because oxygen is going to be utilized to make these oxyanions, and fluoride's not involved. So we got the chloride, the chlorine, bromine, iodine, and then sulfur down to tellurium, it's a mouthful, Tellurium. Anyway, we start, that's the only part of the periodic table that we utilize, okay? And if we look at here, this table kind of breaks it down for you. Everything in blue, starting with the boron, the carbon and nitrogen, these are what we're working with is what is called the parent polyoxy anion. All of them end with the ATE ending, okay? ATE. So, and then from the parent, we're either going to remove oxygens, okay? And most of the time we remove oxygens because 4 oxygens tends to be the maximum. And then we start removing, we don't add anymore, I should say. And then as we remove them, we give it names until we get down to the element itself. And we're back to the IDE, okay? And so everything in blue has 3 oxygens. You can see the BO3, CO3, and the NO3, okay? Also, the table, the BO3, the borate, has a -3 overcharge. The carbonate has a -2, and the nitrate has a -1, okay? Now, everything in yellow, the parent polyoxyanions have 4 oxygens, okay? So silicon has 4 oxygens and so forth, phosphorus and sulfur. So we call it siliconate, phosphate, sulfate as you go across the periodic table. Now, where they differ is their perspective charge. Everybody under carbon in group 4 has a -4, and moving into group 5 has a -3, and so forth, -2. Okay, the ones in green are all the halogens that can be involved in making polyoxyanions. All of them have 3 oxygens for the parent name, the 8. All of them have a -3 charge. And when I put these into a PowerPoint slide, so you can really show it a little bit better. Now I'll pull up the PowerPoint slide here in a bit. Now at the end, you end up with this following table. You have in yellow is the base name, okay? The base name which ends in 8. Now, where'd it go? Notice in this table, there is the base names. You got boronate, carbonate, nitrate, so on and so forth. That is the base name of those polyatomic ions we just talked about. Now, what happens is from the base formula, which is number 3 here, in this case, I use the example of carbon, that name is for that polyatomic ion is a carbonate, okay? Right there. Now, if we remove an oxygen to give us, CO2, now the name, we get rid of the ATE and we add the ITE, okay? Much like sulfate, when we go to sulfite, we remove 1 oxygen, okay? And just the same thing with nitrate. It has 3 oxygens, and we go to 2 oxygens, we've got the nitrite. So removing 1 oxygen, the name goes to ITE. If we remove another oxygen, okay, leaving us in this case with 1 oxygen, so it'll be a CO, the charge remains the same, but it's a CO -2. We add the prefix hypo, so it's become, and we keep the ITE, so that name will be the hypocarbonate, okay? And if we remove that last oxygen, in this case, we're back to the IDE, so it'll be carbide. Okay. Now, from the base formula, not all of these polyatomic ions can gain an electron, but the ones that can, for example, the CO3, we can add another oxygen to give us 4, to give us the CO4 -2. Then all we do is keep the carbonate name, but we add the PER per carbonate. Okay, so in general, we got the base name. If we add a per, that means we have 1 more oxygen to the parent compound, the 8. And if we remove, it goes to ite, and we remove 2 more, it goes to an hypoite. Okay, and this is the one using carbonate. So, and then this table gives you the parent name of all of the atoms that we just talked about, okay? And these are just some, that section of the periodic table you can utilize as a guide to help you can run through it. When I run through the periodic table, you can use these 3 of them, 4 of them I gave you here to practice to make the base polyatomic anions. All right, now at the end of the day, not everybody can, as far as we know, they don't, some of these don't have, these are the ones that we know for sure. For example, nitrogen. Okay, we start off with nitrogen in the far left, just the element nitrogen. When it becomes the ion, it becomes nitride, okay? When it picks up an oxygen, it becomes hyponitride. Picks up two oxygens, it is the nitrite, NO3. And then the one in yellow is the base name, the nitrate. It's an NO3 with a -1. And if the compound does pick up an oxygen, then the name becomes, the anion becomes pernitrate, okay? Now, with a sulfate, we're stuck with 4. As far as we know, there's only 4 oxygens, so we got the pair name sulfate. Remove oxygen, you become sulfite. Remove 2 oxygens, is hyposulfite. Remove those 2 oxygens, you end up with sulfide. I'm not familiar or haven't found or has not been isolated an SO-2 species. Doesn't mean it doesn't exist. As far as you know, I haven't found it yet. You know, as the case of the hyponitrite. All right. And then the chlorides are the same. We got the perchlorate, the chlorate, the chloride, the hypochlorite. We're back to the chloride and then chlorine. Okay. And you can do that with the same with all of the other halogens, the bromate, and so on and so forth. All right. And that's what this Word document has. Now, from these polyatomic ions, you'll notice here, if we add hydrogens back, okay, these negative charges, you know, you have the central atom, say, nitrogen, you have three oxygens around it, okay? 3 oxygens around that central nitrogen that gives the nitrate. Well, on one of those, there's a hydrogen attached to the oxygen, okay? So we end up with sulfuric acid. So what I've done is basically when a base reacts with an acid, you generate these polyatomic anions, the sulfate, the sulfite, those all come from acids. And when they react with the base, they form these salts. And there's a video, I linked there for a video to help name the acids, the corresponding acid that come from these polyoxy anions. Okay. Now let me share with you that table, and we start off with that table, and I gave you 4 or 5 tables there to help you go through and be able to write. Now, what I'm dealing with here is how to create the base, the ATE, okay, the parent-based polyatomic oxy ions. Okay, so we start off with the boron, which is in group 3. Now, eventually, once we add the oxygen, that boron will have a -3 charge, okay? -3 charge. Go across to carbon, group 4, that, just the blue, that carbon will have a -2 charge for that polyatomic ion, regardless of how many oxygens are attached to carbon. The same is true for the boron, okay? And then coming into nitrogen, here comes the nitrogen. Once we add the oxygens to them or remove them, they always will have a -1 charge. Now, everybody in the blue, well, let me start down here at the bottom. Down at the bottom, starting with silicon down to 10, all the ions there will have a -4 charge. Okay, so we got silicon. I haven't showed you how many oxygen silicon will have attached to it for the parent name, but regardless of that, it will be a -4. Next group in will have a -3. So all the phosphorus with the oxygens, okay, will have a -3 for the polyatomic oxy ion. And then next group in, -2, okay? So you can see the sulfate always have a -2, sulfite with the sulfur, -2. See how that's working? And then the last, all the halogens, starting with chlorine, bromine, iodine, once we add oxygen to it to form the parent 8, always have a -1, okay? All right, now, how many oxygens do we have? Well, everybody in blue, the parent name for everybody in blue, the parent would have 3 oxygens. So boron will have 3 oxygens to form the borate. Carbon will have the carbonate and then the nitrate. They all have 3 oxygens with the corresponding negative charge, -1, -2, -3, okay? Now, everybody in the yellow will have 4 oxygens for the parent base name, okay? Now, we don't know for sure, and doesn't mean, you know, they found it yesterday, but for these in yellow, that's the maximum number of oxygens, okay? Meaning that you probably won't find any per 8, but you start removing oxygens, more likely yes, okay? Now, with respect to the ones in blue, yeah, more likely some of them have a extra oxygen, 4 oxygens, but some do not. All right, then finally, the ones in green, everybody there, like the ones in blue, start off with 3 oxygens, okay? So everybody here in this group, either with 3 or 4 oxygens, that is the 8, they all would have the ATE ending in their name, okay? In their name. So we have carbonate, for example, for carbon, nitrate for NO3, and so on and so forth. And so this is, and there's the parent name, I wrote it, orthosilicate, germanate, stannate, phosphate, arsenate, so on and so forth. That's the parent name. Then at that point, the base name, which I wrote number 3, that's the 8 with whatever number of oxygens they have. And then you're either going to remove or add oxygens depending. So in the carbonate case, the CO3 -2, as I described earlier, has the prefix, the ending carbonate. And so you can attach that polyatomic ion with any other metal, sodium carbonate, potassium carbonate. You know, if I remove 1 oxygen, now the name becomes carbonite. And again, any metal partner, sodium carbonite, et cetera, et cetera. And if we remove 1 more oxygen to go to 1 oxygen, it's called hypocarbonate. Okay. All right. And that's basically it. So the video also has a variety of another person talking through this and basically going through the same thing I just did, breaking it down. I just started kind of helping breaking it down here. The majority of the ones that you probably find in the nomenclature exam will be the ones with the halogens, and of course the nitrates and the sulfates. But okay. Any questions about that? Oh, I almost forgot. One more share before I continue. And that is one of the resources I gave you. It is in the module called Additional Chemistry Resources, and it's called the Molecular Polarity. And if you click on it, you end up with this. I hope everybody can see that. I can't tell if it's being shared. Do you see an A and a B on your screen? Yeah, okay, good, thank you. Okay, yeah, because normally it tells me that I'm sharing, and it's not telling me that I'm sharing. So anyway, and I wish they would have put A and A together, 2 similar elements, but that's okay. If we look down at the bottom here, under A, we got the electronegativity. I got a slide scale here. I'm going to shift all the way to the far left for A. And then for B, I'm going to do the same thing, shift it all the way to the far left. So basically, this is an example of 2 atoms that are bonded that have a similar, maybe they're the same, or they have a similar electronegativity. The result is that there's an equal sharing of those electrons in that bond, okay? And what happens is when one starts to increase the electron, if I have another selection, if I take B and I replace B with another atom that has a higher electronegativity than A, we start to see a change in the bond character. Right now, this will be classified as a covalent bond, specifically a non-polar covalent bond, because the electron density is being shared. The electrons are being shared equally between A and B. Okay. Now, if I take A and I replace it with something else that has a higher electronegativity, you see what happens now. B now, its electronegativity, whatever that atom may be, has a higher electronegativity than A. So now it tends to pull the electron density onto itself. And what's happening, the redness signifies a negative, partial negative environment. Because the electron density is being pulled away from A, its electron density negativity decreases, becomes more positive in character. Okay, it doesn't mean it's not negative, but it becomes less negative and has more positive character. Another way to look at this, if you're not familiar with this, I'm sure all of us at one point in time have taken a balloon, okay, and rubbed it on your head, right? You rubbed it on your head, and what do? You put it on your chest. It sticks. It won't stick forever, but it does stick. Or put it in a wall or someplace or it will stick. Now, what's happening there is the following. It has to do with electrons. So your hair, like I stated before, electrons are all around us, okay? Just sitting on the surface doing all kinds of crazy things or not doing anything. You know, don't believe me, or you got a carpet, walk on that carpet and grab your feet and then touch something. Zap, okay? Exactly. And same thing occurs with the balloon, well, similar. I just take a balloon, rub it in your hair, because your hair is full of electrons. You know, some days you wake up with a bad hair day, go boom, right? All that electrical charge is sitting up there. All right, well, take that balloon, rub it in your head, you transfer those electrons that are on your hair onto the surface of the balloon, okay? Now that surface of the balloon has a negative charge, higher electron density than it did before. So it basically has like a large partial negative charge. Now, on the surface of my chest, there are electrons. Like I stated, there's electrons all over. So as I bring that balloon close to my chest, negative charge is pushing those electrons on the surface of my chest away, because negatives repel, right? Just like positives, negatives repel, resulting that on the surface of my chest, I create a more partial positive area. And then when I bring the balloon closer, the result is that balloon sticks. Now, obviously it doesn't stick forever, it's a temporary. And that, by doing this, I created a dipole, a positive area and a negative area, okay? So more on that when we come back, and it has a large effect on the properties. So, but that's a temporary dipole. And that's what happens with nonpolar molecules. They create a temporary dipole. Other compounds that they're two totally dissimilar atoms are bonded together do have a dipole, a permanent dipole. It's not temporary. It is the nature of the beast because those two come bonded. So this could be an example of, say, nitrogen and carbon bond. Nitrogen, being the B, has a lot more electronegativity, so it pulls the electron density toward it, okay? And as I increase my electronegativity, that redness gets even darker, and the blue gets even bluer, more electron density. Now, that partial negative has an effect. If I were to put an electron field around it, the partial negative side will be attracted to the positive plane. Okay, yeah. So that's one way to line up the molecules. Line up the molecules in one's body if you needed that. So that is what a dipole is. Okay, one, and it's very important because now we have a polar covalent bond. Yes, those electrons are still being shared, but it's an unequal sharing. Okay, and that dipole arrow now points from A to B because the B is a lot more electronegative. Okay? This is another way of electron density. Here, kind of showing you that the more electron density going to the B gets a little bit darker in color. All right. Now, there's a fine line that sometimes, depending on electronegativity, it could cause that AB bond to be ionic. Right now it's covalent, but depending on that difference, it can actually go from a covalent into an ionic bond, or at least character of an ionic bond. All right, so that's what that is all about, to help you understand more the concept of electronegativity and what that has when two atoms are bonded together, have a difference in electronegativity, what effect that has on the bond, which then now has an effect on the character of the whole molecule. Okay? All right, so much for that. So yeah, take a look at those resources that help you out. All right, which brings us to chapter 9, fairly short chapter. This deals with acids and bases. Now, I've already introduced you to one base, and that is the hydroxide ion, okay? But the acid is a little bit different. So what I'm going to do is this. I'm going to go to hydrogen. Now, if you recall, hydrogen is in group 1A. It's a nonmetal, but it is in group 1A. Why? Because it has one valence electron. Okay, so its electron configuration is 1s1. That's the very first atom. Okay, recall the s orbit can handle 2 electrons. So hydrogen is very unique, has a very unique property, because hydrogen, this is the hydrogen atom. Okay, the monoatomic hydrogen atom, normally not very stable sitting there. Okay, whenever you have an atom, a molecule that has a lone pair of electrons in there, not very stable. Our body is loaded with atoms that have, molecules that have lone pair. We call these radicals. They're radicals in our body. And they've been attributed to a lot of things happening in our body, aging, destruction, and so forth. So we take antioxidants to get rid of them, to help get rid of them so we can preserve a little better, I guess. Okay, anyway, 1s1 is that one valence electron of hydrogen. And we know that s orbit can handle 2 electrons. So hydrogen has a very unique property in that it can pick up a hydrogen because there's room for it. Okay, and then it fills up that 1s orbital becomes 1s2. And by picking up an extra electron, it really now has a negative charge. And guess what that name is? That's called a hydride. Technically, some periodic tables, hydrogen is not only found in group 1, because the property I'm going to talk about here in a second, but also you'll find it in group 7, because like the halogens, it can pick up 1 electron to fulfill the duet for hydrogen. Okay, so sometimes you might find periodic tables with hydrogen on group 1 and in group 7. Okay, now, like the metals, hydrogen can also lose that 1 valence electron. And in losing that, now has a net positive charge, okay? Because now that s orbital is empty, 0. And only has a proton, electron's gone, and it is called a proton. Okay? So a hydrogen with a plus charge is simply nothing more than a hydrogen atom that has lost its valence electron, and now it is called a proton. This is what is attributes to the acidity of chemicals, okay? Acidity. So a proton is an indication of a chemical being an acid, because in solution, it will release a proton, and releasing the proton, it will be classified as an acid, Okay. All right. So hydrogen is pretty unique in some of the things it can do. So, and this proton is an ion plus charge. Okay. So, and we know that anything that's acidic in nature is sour. Lemons are sour. Okay. Your stomach contains an acid, and if you ever regurgitate, throw up, it burns your esophagus, and it's a very nasty taste. And acid taste is the acidity. The acids are very corrosive. Okay. And what it does, we have some generic pH paper, we call pH paper. What it does is simply just test, it's either off or on kind of switch. If you take with this litmus paper, we have two colors, blue and red. If you take the blue litmus paper and dip it in a solution, it becomes red. It just simply tells you it's an acid. It doesn't tell you the strength of the acid, it just tells you it's an acid. Okay, so anything that's acid, and we're talking about aqueous solutions here. We're always talking about aqueous solutions, water solutions. So any chemical in solution turns litmus paper red, indicate and tell you that it is an acid. Okay. Now at the other end of the spectrum, we have what are called bases. So on one end we got an acid, which produces proton, and on this side we have, on the other end we have a base. And that base is anything that is put in solution and produces these hydroxide ions, polyatomic ion, a hydroxide ion. Okay. Anything that produces the hydroxide ion is classified as a base. Now I wouldn't taste this, okay, but some of these chemicals are very aggressive. If you ever get any liquid plumber, if you ever use liquid plumber at home, liquid plumber is a very strong base. Is utilized at home to unclog your drains because it will dissolve and break down a lot of the greases if your drain is plugged up with greases. And if you get some on your hand, you'll be slimy, feel slimy. You might think it's the chemical. What it really is sodium hydroxide actually is denaturing, breaking down your skin tissue, forming the sliminess. So you wash your hands immediately. It will break down your tissue. That's why it feels soapy, it feels slippery. Okay. In fact, a lot of makeups out there, FYI, are alkaline material. And what that does, you have these things you put on, these masks and so forth, and do whatever you're going to do to your skin. A lot of them are bases, and what they're doing is dissolving the tissue a little bit, okay, to kind of get rid of the old tissue chemically, okay. And sometimes also there are some face treatments you put on your face because you want your face to look a little bit maybe more icky ready. Well, those are a lot of times are acids or something that's acidic. Irritates the skin, irritating the skin causes more blood to go into the surface. Voila, you got a red face. Okay? But all right, so be careful what you use. A lot of these chemicals can be pretty aggressive. All right, as we have blue litmus paper, we also have red litmus paper. And so this solution turns red litmus paper blue. That indicates it is a base. That's all I can tell you. Yes, we do have paper that will give us the range and how strong it is, but we're just simply talking about litmus paper right now, blue or red. Now, here's the thing about, we have two definitions of an acid and a base, okay? Arrhenius, we got a definition of the arrhenius acid and arrhenius base. Now, the thing about the arrhenius, earlier I mentioned to you about there are some ionic compounds in solution will break apart, dissociate, okay? I also mentioned to you that covalent compounds do not. There is one exception, and that exception was acids. And here we are. Because if you look at this particular formula, this is HCl, which is hydrochloric acid. Notice it's hydrogen and chloride, both of them nonmetals, okay? hence a covalent compound. But because the nature of the beast here, and it's classified as an acid, when we place it in solution, it will dissociate. It will break up, okay? And it will break up to generate the proton here and the corresponding anion, whatever it may be. In this case, it's the chloride. This is what's happening in your stomach. We have hydrochloric acid. Normally, hydrochloric HCl is a gas, but by itself, if it was just, not an aqueous system, if it was just HCl, we call this hydrogen chloride, or it could be bromide or iodide. But the moment we put it in some water, this becomes hydrochloric acid. Okay? Hydrochloric acid. And the nature of the beast is such that because of this bond, even though it's covalent, it will dissociate and break up into the two ions, the proton and the corresponding anion, in this case, the chloride. And so Arrhenius came along and said, all right, anything that in solution produces a proton is classified as an acid under the Arrhenius definition of an acid. Okay. He further went on to define a base and stated that any chemical, notice here, in this case, this is covalent compound. But a base, in this case, is ionic, specifically a hydroxide ionic compound. So any ionic compound that, when put in solution, dissociates and produces the hydroxide ion is classified as a Arrhenius base, okay? So Arrhenius base produces a proton, Arrhenius acid produces a proton, and Arrhenius base produces an hydroxide, okay? So this example here, this is like almost 100%, very strong. But there are some examples where it's not so much 100%, but nevertheless, it's still a base because it does produce a little bit of the hydroxide ion. Okay, well, here's your introduction to, remember, I mentioned this, I'm pretty sure I did. I said we're going to talk about chemical reactions. And of all the chemistry out there, there's only 6 types of chemical reactions. I may have mentioned when you drive your vehicle, you burn something, that's a combustion reaction, okay? Now here's this type of reaction. This is called a neutralization reaction. And it's simply the reaction of an acid and a base, okay? Now the net reaction, meaning only the chemicals, the parties that are actually doing anything, that's the net. Of the other guys, the partners that are involved in this reaction are just sitting there, just holding the charge constant. They don't do anything, okay? They're just sitting there. And so in this case, we have HCl, which is an acid, okay? And sodium hydroxide, which is a base. So the net is this. HCl in solution will produce the proton, okay? Sodium hydroxide right here in solution will produce the hydroxide ion. And when the hydroxide ion gets together with the proton, guess what you produce? Water, which is neutral, okay? Hence the neutralization reaction. So when you get an acid and a base, you always generate water and then the corresponding salt, whatever the salt may be. Now, you might think, in this case, it happens to be sodium chloride, and that's what we tend to think at times, that sodium chloride is the salt. But remember, any ionic compound is a salt. It could have been potassium chloride, it could be magnesium chloride, it could be any chloride. It's a salt, it's an ionic compound, okay? All ionic compounds are salts. We're not just limited to, table salt, sodium chloride. All right, so You might ask, well, wait a minute, how does that happen? Well, let's think about it for a second. If we draw the Lewis dot structures for the hydroxide, we will find that there are 3 lone pair of electrons on the oxygen, okay? Now remember the first example I said the hydrogen had a 1 valence electron and we have 1s1 orbital. That when it loses that 1 electron, it becomes a proton, and that orbital now is empty. So here comes hydrogen with an empty orbital, okay? And guess what? One of those pair of electrons on the oxygen can then go into the empty orbital of hydrogen and create a bond. And that bond now is, remember the Lewis dot structure of water. Okay, now we created a bond between the oxygen and the hydrogen, okay, because hydrogen had that empty orbital and the hydroxide had an extra pair of electrons sitting out there with negative charge. And now when it comes in, boom, they can form the bond to form water, okay? So, and this is true for any acid-base reaction. It's, you can try this at home. Vinegar is a base, acid. Sodium carbonate is a base. You mix them together, you get a bubbling action. The point being that they neutralize. That bubbling is just carbon dioxide. All right. Okay, now that definition lasted for a while. Proton generator, hydroxide generator for an acid. But later on, it turns out that there's a lot of chemicals out there that have nothing to do with protons, okay? Nothing to do with protons. They don't generate, are hydroxides. I should say that. Let me restate that. I don't want to confuse anything. So we have an acid that produces a proton. But when it came to bases, there's a lot of bases out there that have nothing to do with the hydroxide, okay? They don't generate a hydroxide. But they do interact with the proton to neutralize it. So a new definition had to be created that would encompass more examples of chemicals that can be classified as bases, but yet had nothing to do with generating a hydroxide solution when they're in solution, okay? And hence, the newest definition would be the Brownstein-Lowry definition. Now, what they both have in common is this. For an acid in Arrhenius acid or the Brownstein-Lowry acid, technically are the same thing. In both cases, the Arrhenius acid produces a proton. Here they say it loses a proton, whatever. A proton is generated. Okay, so in essence, about the same definition. Where they differ is with respect to a base. Where the Arrhenius base produces a hydroxide ion, the Brownstein-Lowry base is any chemical that will accept that proton, okay? You accept that proton. Now, recall I just did that example of the hydroxide and the proton coming together. That proton had that empty orbital, and that pair of electrons from the hydroxide came and inserted into the empty orbital of the proton, generating water, right? Well, in this case, it's very similar. The difference is we have chemicals that have lone pair. Now, recall, I'm going to talk about this and we'll call it. Okay. Remember we had the Lewis dot structure of hydrogen, of ammonia, NH3. Recall that we ended up with a lone pair on the central atom, okay? This is the acid. It will produce a proton. An empty orbital, again, is there. And so there's a lone pair on the nitrogen that proton can interlock with and generate a bond, okay? Generate the ammonium ion, okay? We end up with this, we did the Lewis dot structure of this too, the ammonium ion. See here, that lone pair ties up that proton. So now it has a plus charge, and it renders that proton neutralizing. Okay? And so now anything with a lone pair that does not necessarily produce hydroxide can be classified as a base. Even a hydroxide, if you think about it, the hydroxide is sitting there, like I explained earlier, it's sitting there with a lone pair, and it's doing the same thing. So it could technically be classified too as a Brownson-Lowry base. Okay. All right. So with that in mind, there was more chemical compounds. These compounds with nitrogen are generally called amines, A-M-I-N-E, and there's a lot of them out there. Okay. And they can act as a base, specifically a Brownson-Lowry base, okay? Not a Arrhenius base, because the ammonia doesn't produce any hydroxide. All right, so tell you what, let me stop it here. I got 3:32, I went over a little bit. Finish chapter 8, 9, up to 7. All right, so we'll be done with this one on Thursday, and then we should give you plenty of time to prepare for the next exam. Okay? All right.